Okay, let's look at another example. Okay. I like this one. I'm just going to focus on calculating the first moment of area. Okay, understand? So for this problem, we have a vertical shear force. Okay, coming out vertical. So we are asked to find the shear force at point A and the shear force at point B. Okay, so you can find this is A and this is B. Okay, and it can get a bit confusing. Okay, so now we are going to what? We start by sketching your what? By sketching your shear flow. Okay, now now this you can get from your. I post this on Avenue to Learn already. Okay, so now we look at this. Okay, so I'm just going to focus on drawing the top half of the structure. It's because the first moment of area cannot cross the what centroid. So I'm going to draw the top half. Okay, so bear with me. So I'm going to sketch the top half. So we have this. I deliberately make it thicker or no, let's not confuse me. Then we have this. Then we have this. Okay, then I draw a green. Over here. This is our what? Centroid, right? So now this is our point A. Over here, this is our point B. Okay. So we have a shear flow coming down here. This is our Vy. Sorry, shear stress. Okay. So the rules still apply, right? The rules still apply that the Q is going this direction. Okay? So I'll design the top. Okay. Now the fluid is coming from the top, come down here, right? And we realize that point A is easy. Agree or disagree? Right? Point A is easy because point A, the first moment of area is this yellow thing. I'm shading. How about B? Okay. So if we draw the shear flow at B, right? Now, if I draw the shear flow at B, it will coming in from two directions. And I'm going to draw the axis where B is coming down from. So now this is coming in this way. And then it meet down here. So at point B, what is the first moment of area? right? It can get confusing now, yes or no? So this is the correct design of the what? This is the correct design of the this is the correct design of the shear flow. Okay. When both left and right shear flow are coming in, meeting in, means at that point is equal to what? 0. So over here, at this point, the terminal, the shear stress is equal to 0. So because there's no area, right? You have flow coming in from one side, you have flow coming in from the other side. It's also equal to what? 0. Yes or no? Right? So how do you take your first moment of area now? We still need to apply our rule, still stand. The first moment of area cannot cross, still stand. Okay. Our first moment cannot cross the centroid is still valid. Okay. The analysis is start from outside is still valid. Okay. But where is the area that we're going to concern now? Okay. So the area of concern is also relative to the terminals. So down here is our terminal. Over here, this is also our what? Terminal. So for point B, the area that we're going to analyze is this area. I want you all to hear me out, okay? This is the stage where it's confusing, okay? But I want you all to hear me out. In terms of fluid flow, okay, in terms of fluid flow. Take it as the two vertical webs, okay, the two vertical webs are your mainstream. You understand what do I mean by mainstream? It's like where the shear flow will want to go. It does not want to go, okay? It actually don't want to come in, okay? It wants to go down the mainstream, okay? At the top, it's also the mainstream because this is where the terminal is coming, it's flowing down this way. Over here, once it does not really want to come into the center at all because the mainstream of the flow wants to go down, okay? So for this case, the first moment of area to take is this area. It is not, if we apply to our old logic, it should be what area? It should include this area, and this area. Yes or no? Right? But no. Right? Over here, we also have a what? A terminal is defined whether both shear flow come together or it ends. Okay? So you can see over here, the shear flow are coming to the center. So for this case, when we calculate our shear flow, when we calculate our first moment of area, we only calculate this section. Okay? We only calculate this section over here. We only calculate this section over here. So I'm going to show you how to calculate the shear flow at point B. So let me have the So the shear flow, the Q at point B, the first moment of area at point B. Okay, looking at the diagram. Okay. So the width is 125. The depth is 10. Hey, 125, I write 120. You know, today like my hand is not listening to me. 125. The depth is 10. The Y bar is 110 minus by 10 divided by 2. Okay, so 110 minus 10 divided by 2 times by 10. Hey, 110 minus 10 divided by 2 times 10 times 125. is equal to 131.25 times 10 to the power 3 meter cube, or 131.25 times 10 to the power minus 6 meter cube. So that is the first moment of area, and the thickness. The thickness is what? 0.01. And the Q, okay, this is what? This is because the terminal, both arrows are coming to the center. You got one Q over here, you got another Q over here. So when you write your formula, your shear stress, okay, shear stress. So the shear stress direction is x plane, z direction at point B is equal to Vy. So our Vy was what? 18 times 10 to the power 3 divided by Iyy, Izz, multiplied by 131.25 times 10 to the power minus 6. We know that we have to divide by 2. This 2 is because it is a what? Box beam. Right? Because you got 2Q coming in, so it's a box beam, multiplied by the thickness of 0.01. Okay. So I'm not going to compute this out. I'm just going to look at the solution. Okay. So I've also posted the solution. Okay. Copy. This is what the solution is for. The solution is not to make you understand. Okay, it's to help you to check. Okay. So let me string it down so we can come on, Eugene. Seriously. All right. My apologies, okay, for disturbing your copying. But you stupid thing, paste. Okay. So we look at, I'm going to zoom in, okay. So we're going to look at point B. So how the solution present itself, right? So you can see that this is also equal. I want you all to see that this is also equal to, can you all see or no? Right, this value over here is the same with what we have. They put half down here is because of a box beam analysis, and the thickness is, yeah, the thickness is also the same. 10 times 10 to the power minus 6, 0.01. Yes. Yep. Yes, it's because of that terminal over there. Because anything comes to the terminal, it will equal to what? 0. Okay. Now, so I'll have another quick example before we finish the topic on thin wall. Another one. Okay. So yeah, regardless. Okay. So let's look at this one now. Let's look at this one. Okay. Okay, let's look at this one. So over here, right? Right, over here, you also, so they ask us to calculate the shearing stress at point B, right? The difference with this is now the centroid is where? The position is below the what? The centroid. Okay, so I'm going to sketch this out. Okay, I'm going to sketch this out. Right? So we are going to, I'm going to sketch this out. So we still have this, right? So this is slightly different because now Okay, now the centroid now is over here. Okay, so over here is our centroid. So we still have our dy over here, right? So now we are going to design the flow. So again, the mainstream flow is coming from here. Right, the mainstream, these are the mainstream. Okay, mainstream. This is like our highway 401. Okay, everyone wants to go there. At the center is Waterloo. No one wants to go there. There's something wrong with the toilet water. I think I have to edit that. I'm online again. Shoot, it's okay. Right, again, for this case, if we want to find point B, what is the area that we are concerned with? Right, because we have a terminal here, we have another terminal here, right? So we know at the terminal the shear stress is going to be what? 0. So the area of consider is the one that shaded in yellow. Okay, I've gone over time. I'll see you guys at what time? 10:30. Okay. I hope you all will embrace this. Yeah. Now you have to watch the what terminal. Now, for this topic, this is the most difficult. Okay. You can do any questions in any textbook now. Okay. I'll see you all later. I do apologize.